So what I was planning to do today is just show you guys some practice problems. If you have started the homework that's due, we can always, maybe take some questions ahead of schedule a little bit, see how you're coming so you're not stressing about it later. So that's another thing that we can do, but I just wanted to do some practice problems. I put another practice quiz up on the website. I don't know if you guys have been looking at those. If you scroll all the way down at the bottom below the group works, each week I'm kind of putting just like a one-page quiz that's not really... The quizzes that I'm putting up there are harder than the one you're going to take on Monday. The one you're going to take on Monday is just going to be definitions and propositions and stuff like that. The questions that are on those weekly practice quizzes, you actually have to work them out, think about them a little bit. I really like those problems. So one of the first things to do when you're studying for the in-class part of the test will be to take a look at the practice quizzes, as well as the group works and all of that kind of stuff. So anyway, so we could even look at some of those today as well if you guys are interested. But I just thought maybe we could use a little more practice. Some of you guys are having some problems with writing the proofs, I feel like, in a way that is really mathematically rigorous, and it's just going to take a little bit more practice. You're just going to have to work hard to kind of get there. So I brought several problems we can work on for an hour and a half or whatever, see how it goes, and then I'll see if you guys want to ask me any questions as well. Okay? So let me start off here with the first one, and I'm going to try to make this pretty easy to start off with. The first one's going to have a few parts. It's just going to say, does D define a valid metric on X? So I'm going to give you some examples of this, right? So the first one, part A, I want to take r squared. Oh, and if you know the answer right away, just keep it to yourself a little bit. I would let everybody just think it through. Don't blurt it out immediately. So let's take the r squared and let's do this formula here. The distance from xy to AB, I'm going to define it to be the min of the absolute value of x minus a and the absolute value of y minus b. So let's just take that as an example. And how are you doing, Zane? I've got your homework here somewhere. No. I've got some solutions posted. Yeah. Oh, she made it. There you are.
Thank you.
Wow. More popular than I thought. Okay, so we just started, guys. We're just doing some practice problems. We talked about changing the date for the exam and the take-home and everything, and I can tell you about that later. But the idea here is I'm just going to throw some problems at you that I could ask this question on the in-class part of the test or the take-home part, either one. So I say, does D define a valid metric on X? So we're taking the xy plane, and we're measuring the distance between 2 points in the xy plane by this formula here, the minimum of these two numbers that are right here. Okay? So the question is, does that define a valid metric or not? So I'm going to give you 30 more seconds to think about it, and then we're going to see if anybody wants to answer. So the minimum of, you look at the first coordinates, how far apart they are, then you look how far apart the second coordinates are, and you take the minimum of those. So we have to remember the axioms, right? For a metric, this is one thing that you guys hopefully know. How many axioms are there?
4.
4, okay. Can somebody tell me the first one?
The distance between x and y is greater than 0 for all x and y.
Okay, great. So any 2 points have to have a distance that's at least 0. Okay, what's the second one?
The distance between x and y is the same as the distance
Great. The distance doesn't matter what order you put the points in. Okay, what's the next one?
Distance of xy is equal to 0. If only if x is 0.
Great. All right, and then the last one.
Distance of x to z is less than or equal to distance of x to y plus x distance of y to z.
Great, exactly. This is going to be for all x, y, and z and x, right? Okay, sounds like some of you guys have been studying for the quiz. We got all the axioms of a metric down. Perfect. Okay, so based on that, how many of you, do we have an odd number here? No, we have an even number, so there could be a tie. But how many people think, yes, this is a valid metric? Okay, how many people think, no, this is not a valid metric?
I have to work out 4.
We need to think maybe a little, do you need how many people want another minute to think about it?
Yeah.
Okay, take another minute, let's think about, now that we have the axioms written down, let's think through the 4 axioms and kind of go from there. Is this your drink or mine?
Oh, that's not mine.
Okay, it must be mine. Okay. I'll give you guys another minute to think this one through. Are you okay back there? Yeah, no, you can see. Okay. How many people feel a little more confident that they know the answer now? Okay. Maybe sort of kind of. So maybe I'll jump in here real quick. Of course, if you put the word max here instead of min, then we're talking about one of the metrics that you saw in the book already, and that was a valid metric. So the question is, if I change the max to min, does it still work? And you know, really, I don't have any magic recipe for this. I usually just go through the axioms, go down the list and see if they work, right? So let's just check these axioms here, but let's think about the first one. If I use this formula right here, will I always get an answer that's at least 0?
Yeah.
Yes.
Definitely, because this is at least 0 and this is at least 0, so whichever one is smaller is still at least 0, right? So this one is yes, right? Okay. Now I didn't write anything down yet because I'm trying to figure out what is the correct answer to the problem. Now, if it turns out that this is a valid metric, then I should go back and write out the proof of it. I shouldn't just say it out loud. I have to write something down. Okay, but let's just get a feeling for this first. How about the second one? This one is the one that says if you switch the positions of the 2 points that you're measuring the distance from, then you should get the same answer. Now, if I switch the positions, it means that the x and the a are going to swap roles, and the y and the b are going to swap roles. Will I get the same answer?
Yeah.
I will, right, because x minus a is the same as a minus x after I take the absolute value, and so is the second slot, right? Okay, so this one's looking good as well. Okay? The third one says that the only time that the distance between 2 points can be 0 is if you take the same point twice, basically. Is that one going to be true?
Yes.
But you,
It's true?
yeah.
Yes.
Which one, number 3?
No, I'm
Yes.
looking at number 3. 3 is true?
Oh, no, because if the y's, if the y points were equal, but the x's weren't.
Exactly.
Yeah.
Exactly. This one does not work because I can give you 2 different points that have a distance of 0. For example, now, so if the answer is no, then what you need to do is give me an axiom that fails. So in this case, the third axiom we came to is the one that isn't working out. And then I should actually give an example. So can you give me a specific, and when something's not true, a very specific example is all you have to give me. Can somebody give me a specific example?
0, 1, 0, 2.
Okay, 0, comma 1 and 0, comma 2. That's 2 different points, but what is their distance? Well, it's going to be the minimum of 0 and 1, right? Which is 0. Okay? So you have 2 points that are a distance 0 apart, but the points themselves are not the same. There we go. So this is not a valid metric. Do I even need to go any farther into my study? No, I'm done. I can stop thinking about it right there. Does this make sense? You're pretty good with that? Okay. Let's try another one. Practice a little bit more here. Let's take x to be the set of functions from the closed interval 0, 1 to the closed interval 0, 1. And we've used this set before, just like calculus functions. But I'm going to give you a metric that you haven't seen before. So let's suppose that I'm going to measure the distance between f and g a different way. In the past, we've used a supremum of the absolute value of f minus g. Let's do a different formula this time. I'm going to do an integral. An integral from 0 to 1 of the absolute value of f of t minus g of t dt. Okay? So this is a different formula than you've ever seen before. So I'm going to once again give you guys a little time to think about whether that is a valid metric or not. And we'll take another vote. You don't necessarily need to write a lot down at the beginning when you're first, maybe just some scratch work is all you would need. You're just trying to get an idea at this point. Okay, so we're not trying to prove the answer so far. We just want to know, is it yes or is it no? And so we can kind of just look at these 4 axioms and just kind of think about them a little bit. And, instead of getting too wrapped up in a detailed calculation, it might be a good idea. What do you guys think about the first axiom? If I took any 2 functions, will this always be at least 0? It will, right? And that's because, you know, you're taking the absolute value here, so this function is above the, it's above the t-axis, so when you integrate a positive function, you get a positive area, right? So this is like the area under the graph of a function that's positive, right? Okay, so the first one, let me just erase my previous marks here. So the first one seems to be okay. If I switch where the f and the g go, if I go back and forth, and switch the f and the g, will I get the same answer?
Yes.
Absolutely will. Okay, great. How about the third one? Obviously, if you put f and g to be the same function, you'll get 0 inside the integrand. If you get 0, does that force f and g to be equal, or could they be different from each other? Or let me say that differently. If f and g are different, will their distance be greater than 0?
Yes.
Yes.
Okay, so you can think about what the functions might look like, yeah? So you have, 0 and 1 and 0 and 1. So you have these two, here's a function f right here. If you took a different function, if g was not the same as f, maybe it was almost the same as f, but it was mostly on top of f, but it's a little bit different function, then when you subtract them, right, are you going to get, there's going to be some area between the two, right? So this is going to therefore contribute positively to the total area, and you can't ever subtract it back out. It can't cancel out. Nothing can cancel out here because you're only integrating something that's at least 0. If it was possible for it to, you could have some graphs that were overlapping and somehow the area is kind of canceled out or whatever, but you're taking the absolute value of these functions before you do the integration. So you actually are integrating something that's at least 0. So this one should be okay as well, right? This should be okay as well. And then what about the fourth one, which is our triangle inequality? Do you think that will be true?
Yes. You can add, subtract the same function and split up the
Basically, this axiom works for absolute value, and so that's really what this metric is requiring you to do, is to make it work for absolute value, because that's what you're doing here. So it makes sense. My intuition would be that yes, it does work, because it's really just requiring the same property for absolute value. So yeah, so it seems like, at least on the first pass, kind of thinking through the 4 axioms, it seems like the answer is going to be yes. So let's go ahead then and let's just try to write something to kind of help justify that, okay? So I'm going to just write down the axiom, and then I'm going to explain a little bit. The first one, very simple. You just simply have to say, since absolute value of f of t minus g of t is always greater than or equal to 0, right? That's a positive number. Then the integral of that, the integral of a function that is not below the x-axis, has to give you an area that's greater than or equal to 0. There's not much to say there. I think sometimes people are uncomfortable. They're like, I didn't show enough calculation or enough work. That's all you have to say. That's good enough right there. Okay? So because the function that you're integrating is non-negative, the total amount of area under that graph of that function will be non-negative. That in words is what you've said right there. Okay? You could say that in words, like that sentence I just said out loud. You could just write that too if you preferred to, but this gets to the essence of it a little bit quicker. Okay, the second one we really can show just an equation very simply. You just start with the distance from f to g. You write down what the formula for it is, the integral of the absolute value of f of t minus g of t dt. And then what am I going to want to do in the next step?
Switch G and F.
Exactly. I'm going to switch where the positions of the g and the f are. Okay. And now what you have there is just the distance from g to f. Okay, so basically, because the same exact axiom is true for the absolute value, you can use it here as well, because the integration just kind of floats through the calculation. It's not really the key piece of it. Okay. All right. Slow me down. By the way, this is very casual. We're in no hurry. It's just kind of a fun day to just practice some problems. So ask questions. Slow me down as much as you need, as much as you want to. The third one, I just want to say a quick comment about this third axiom. It looks like an if and only if, like you've got to prove things two directions. The backwards direction is always pretty much trivial. If x and y are the same, then the distance between the point and itself should be 0. That's just, you can see right here, clearly, you can write this down. The distance from a point to itself, if you plug it into the function, is just going to be the integral from 0 to 1 of 0 dt, which is 0. So this is kind of what I would write as the backwards direction of number 3. Usually the backwards direction of number 3 is like totally trivial. And where we have to actually do something is to prove the forward direction. So the way I like to usually prove the forward direction is to say, well, if x does not equal y, then the distance between the 2 points is not 0. So it's easier to phrase things when you, for proving the forward direction, I find it easier to phrase the contrapositive. So, if f does not equal g, right, then that means that the absolute value of f of t minus g of t is strictly greater than 0. It can't be negative. So
you use the contrapositive?
yes,
Okay.
that's a contrapositive, exactly. So then this has to be greater than 0 for some t in 0, 1. It doesn't have to necessarily be greater than 0 for all t, but at least at one point, at least somewhere in that interval, the two functions have to be different. So this has to be strictly positive, which means you're now going to collect some positive area under the graph. And as I said before, it never cancels back out again, so the final result will have to be a positive amount of area. So thus, the integral from 0 to 1 of f of t minus g of t dt would be strictly positive. Okay, so that would be good enough to explain that. Okay. And then the fourth one is usually the hard one. It's definitely the messiest one, because you've got to have 3 terms here to look at. But what you're going to want to do for that is, let's just say we take f and h. We're going to use f, g, and h here. You simply write down the formula here for the distance between f and h. Start with that. And then what I'm going to do is, this is what Zane already basically explained how we would do this, is what we can do is the same trick. It's exactly the same trick that we would normally use if we just had absolute value there, which is that we insert into the middle of this a g of t by just adding it and subtracting it right next to each other. Basically is like doing nothing. You guys have all seen this kind of trick before, right? Mm-hmm. It's kind of a standard way of breaking this up, because see now, now what you can do is you can just use the inequality. I'm not using anything about integration right here. I'm simply using this property of the absolute value. So you can split the absolute value. That's actually axiom 4 for the regular absolute value metric, right? And now you can just use the fact that integration respects addition. So this is just the integral from 0 to 1 of the absolute value of f of t minus g of t dt, plus the integral from 0 to 1 of the absolute value of g of t minus h of t dt. And that is exactly what you want. This is the distance from f to g plus the distance from g to h. Okay. So that is the fourth axiom. I'm going to erase these axioms now. I'm assuming that you know what they are. Alex, what's going on?
I have a question about axiom 3. So it turns out, like, if you take the integral of a function and it's 0, that's if and only if the function's equal to 0 for all the finitely many points.
Correct. I wondered if you might ask me, I'd actually thought that might be what you're going to ask me.
Yeah.
If there's a set of measures 0 in the notion of measure theory, then you can displace a finite number of points without changing the value of the integral. There's an easy way to fix it,
Yeah.
which is to just change my metric space slightly and just assume that this is continuous
Yeah,
functions.
yeah, that's what I was gonna
Yeah,
say.
so if I just say this is the set of f continuous, okay, for the record, since this is a video that's going to go up on YouTube and I don't want to be accused of saying anything wrong, this is, let's make this metric space the space of continuous functions on the closed interval 0, 1 to 0, 1. Alex is familiar with a very subtle point about, no, so in other words, if you integrate a function, let's say I integrate this function right here, here's from 0 to 1, like that, obviously the total area is 0. If I take one point and I pluck it off of the x-axis and plot it up here like this, maybe you remember from 350, if you move a finite number of points off of whatever you're integrating, it doesn't change the value of the integral. But I could now say that I have a different function than just the 0 function. So this would be, this would be f not equal to 0, but the integral of this function f, even with this one point right here, see there's no area there because there's no thickness to that point. That integral is still 0. Okay, but of course this function is not continuous, and that's why if I had said continuous, you wouldn't have had a problem with it. Yeah. Okay, good question though. Thank you. All right, everybody okay with that one? Okay, let's do one more of these. Okay. Do one more. I've erased the axioms, but that's okay. Let's take x to be the natural numbers. And let's take the distance between 2 points x and y to be the square root of the absolute value of x minus y. Okay, so give yourself a minute or two to think about whether you believe that's going to be a valid metric or not. Talk about it. Go get another color. By the way, so if I ask you what is the square root of 9, right? I hope everybody knows the answer is 3. It's not plus or minus 3. When you take a square root, the definition is it's always the positive root. Now, if I say what are the solutions to this equation, now the solutions would be plus and minus 3. But in terms of a square root, you only take the positive value. So that might be relevant here a little bit. What do you guys think about the first axiom?
Yes.
Looks pretty good. Okay, I'll start writing that down while you guys think about the rest of it. Really not much to say. Just more or less just write that down. Okay, what do you think about the second axiom?
Yes.
Does that work? Okay. Let me see if I can write that one down.